In this lecture, we'll learn how to handle strings of characters. There are instructions in RISC-V to manipulate characters. They load and store a single byte at a time instead of loading and storing a whole word. They are very commonly used for the processing of strings. And one example of such an instruction is the load byte instruction, or LB. And what the load byte will do is to take a single byte from memory and sign extend it to 32 bits and then store that byte into the register. So let's look at an example. Here's some memory, and notice that the distance between the position in memory is 1, so there is 1 byte in each position. We have the values for the different positions in memory, and let's suppose the register S0 contains that address, and I issue the instruction load byte 0s0lb. So I'll be loading the byte 0x09 into the register T0. So what will going to happen is that that byte will come and will be sign extended to 32 bits. In this case, the sign bit is 0, so the sign extension will add zeros to the upper part of the number. Let's say that now I do the instruction LB from 1s0 to T1. So now I'm loading the value 0x80 into the register T1. So this time, the byte 80 comes from the memory and is sign extended to 32 bits. So the upper bits of the byte will be all ones. Another instruction that we have for manipulating bytes is the LBU. The LBU 0 extends the 32 bits into the destination register. U stands for unsigned, so that this is the load byte unsigned instruction. As an example, if we load the same value 0x09 into T2, the 0 extension will add zeros to the upper bits. But if we load the byte 0x80 into T3, that value will now be 0 extended to 32 bits instead of the sign extension that happened in T1 when I use a load byte. So that's the difference between using a load byte and a load byte unsigned instruction. We also have a store byte instruction. The source register for a store byte has 32 bits, but the store byte is storing only a single byte. The byte that is stored is the least significant byte, or the rightmost byte when we write the 32 bits. There are instructions also to manipulate half words. A half word is 16 bits instead of 8 bits. It's the half of the word, and they're similar to the load byte. There is a load half word that sign extends the 16 bits into 32 bits. There is a load half word unsigned. The 0 extends to 32 bits. And then there is the store half word that we store the rightmost half word, or the least significant half word of the source registers into the memory. One interesting question is, when I'm accessing an array, by how much do I need to multiply the index of the array in order to get the address of a given element of the array? Let's look at the size of each element of the array. So if I have an array of integers, like this one, int x 100, so I have an array of 100 integer elements. Each element of the array will contain 4 bytes. And when if the base of the array x would be, for example, at 0, what I'll be doing is keep counting by 4 to find the next elements of the array. So the first element is at 0, the next element at 4, and then at 8, at 12, and so on. If I want to compute the address of the position y of the array, what I need to do is to take the base of the array, x, which is the address of the element 0 of the array, and then add 4 times I to that value to obtain the address. How about if I have an array of characters, such as char s100? In this case, each element contains a single byte, is contained in a single byte. And when I want to go from the 0 element into the first element of the array, all I do is to increment 1. and successively for the other elements. So this would be like skip counting by 1, that is just counting. So the address of the position j of this array is given by s plus j. How about if I have an array of doubles? This is how I declare an array of doubles in C. And a double occupies 8 bytes. Therefore, to go from the element 0 of the array to the element 1 of the array, I need to advance by 8. So this is like skip counting by 8 to find the elements of the array. And to compute the address of an element of this array, I need to take the base of the array and add 8 times k to that base to find the element f sub k. I can use memory to store any type of data. For example, in C, we have types that are aggregated data structures. Here's an example of a type called city that has 4 fields into the structure. And the first one is an integer, which will be 4 bytes. The second one is an integer, another 4 bytes. Then I have 2 chars, each one is 1 byte. Therefore, each element of each structure of each city will occupy 10 bytes. Now, if I have an array of cities, so that is illustrating in the upper right corner there, the structure, how the structure will be laid out. I have 2 integers and 2 chars to form 10 bytes. If I now have an array of cities, the question is how much do I need to advance to go from city 0 to city 1? And in this case, it will be 10 because each city is 10 bytes. So in this case, I skip counting by 10. And to compute the address of the position I of the array T, I will take the base of the array T and add 10 times I to it. So these examples illustrate that the amount that I multiply an index by depends on the size of the type of the array. So a quick recap of this first part of this lecture. We have learned that there are load byte and load byte unsigned instructions. And the difference is that the load byte does a signed extension, while the load byte unsigned does a 0 extension of the value. And there are equivalent words for load half word and load half word unsigned. We have a store byte and a store half word that will always store the least significant bits of the source register. We have also learned that the amount that we have to add for each to find a given position of an array is the value of the index at that position multiplied by the size of the element of the array. So for an integer, it will be in the example here, x plus 4 times I, for example. For char, it will be s plus j. And for the array of cities that I have here, it will be t plus 10 times k. So this is what we had for this part of the lecture. In the second part of the lecture, we'll look into how to implement a string copy function.